All right, this is going to be the first of two parts related to chemical composition. So we're going to hit some basic chemistry review in this particular lecture, and then we're going to tie it into how it's going to apply to us in mass and energy balances. So the first thing that I want to remind you is that physical properties of a mixture depend on its chemical composition. Throughout the semester, you're going to see multiple species and multiple different molecules getting mixed together, and the chemical composition is going to influence the physical properties of the mixture. So if we have chemical reactions occurring between multiple species, it's going to manifest in a physical property related to that species. Another concept that we want to make sure that we remember is atomic weight. So remember that atomic weight is the mass of an atom based on assigning a carbon-12 atom the mass of exactly 12. So atomic weights, right, are related to the specific atoms on the periodic table. So if we say that carbon-12 is equal to 12, every other atom is in relationship to that. Molecular weight is the sum of atomic weights of elements in a specific molecule, and that's really important, right? So things like H2O, right? That is a molecule, not an atom. There are 2 hydrogens and 1 oxygen. So the molecular weight is going to be the atomic weight of hydrogen times 2 plus the atomic weight of oxygen. And these are specifically in compounds. And we use the periodic table to calculate molecular weight. So you're going to need access to a periodic table throughout the semester, and we do have a periodic table posted on Canvas in the resources. We also want to review the concept of a gram mole, which we use the units of mole in this particular class, and that's the amount of species whose mass in grams is numerically equal to its molecular weight. That's how a mole is defined. As an example, carbon monoxide has a molecular weight of 28 grams per mole. Carbon has a molecular weight of 12, oxygen has a molecular weight of 16. So as a result, you add the two up to get that molecular weight of 28, and that means that 1 mole of carbon monoxide therefore contains 28 grams. That's how a gram mole works. Molecular weight is going to be important for us in this semester because it's used to convert between mass and the number of moles of substance. Now that's really critical because we're not just going to see mass flow rates, we're also going to see molar flow rates this semester. So as an example, take a pause and see if you can calculate by yourself how many kilomoles there are in 34 kilograms of ammonia. Let's take a look at the solution for that. So if we have 34 kilograms of ammonia, we can go and we can find the molecular weight of ammonia as 17 kilograms per 1 kilomole and get 2 kilomoles of ammonia out. So remember that it is grams per mole when you're pulling it off the periodic table, but it can also be kilograms per kilomole because you can have 1,000 grams as a kilogram, and you can also have 1,000 moles as a mole. So just remember that that's possible, that you can have kilograms per kilomole as well as grams per mole. And then lastly, 1 mole of any species is going to contain approximately 6.02 times 10 to the 23rd molecules of each species. And if you remember from chemistry, that number that you see there, the 6.02, that is Avogadro's number. That's the way that we go from moles to molecules of a species. So as a little bit of review, we have an example problem here. This is going to be example 3.1, and this is a chemical engineering style problem. We want to convert between mass and moles. So we want to know how much of each of the following are in 100 grams of CO2, which has a molecular weight of 44.01 grams per mole. So what I want you to do is I want you to pause the video and I want you to give this a try yourself. We're going to have the solutions to this problem in a separate video, so you can skip ahead in the solution if you feel really good about this. So you don't have to watch the video if you feel like this concept is really strong for you. But if you're not sure about your answers, I would recommend watching that solution video. But this is an example for you to try on your own to make sure that you understand this concept. All right, next thing that we want to make sure that we talk about is why we care about moles in this specific class. So the big reason that we care is that molecular weight can be used to relate the mass flow rate of a stream to the molar flow rate of a stream. So as an example, let me grab my laser pointer. The mass flow rate is something in terms of kilograms per second, and we use an m with a dot over the top for mass flow rate. And that's going to be equal to the molar flow rate, which is an n in this class with the dot over it, times the molecular weight. So whatever is in brackets on this screen is going to be the units. So you can see that a kilomole per second times a kilogram per kilomole will give us a kilogram per second. So that's the way that we convert between mass and molar flow rates. And this is really important because when we have different streams mixing in a reactor, moles might be the better unit to use because we are going to have chemical reactions occurring at the same time. So we can generate products or we can consume products in a system. And so moles is actually going to be better in those situations many times. We do have another unit sometimes that you might see in the future called a Dalton. A Dalton is defined as 1/12 the mass of a carbon-12 atom, and this is primarily used when we talk about biochemical species molecular weight. So you may encounter this unit later on in your studies as an environmental engineer. We're not really going to use it in this class, but I do want to point it out because it does come up in Environmental Engineering 322, which is our Biological Principles of Environmental Engineering class. So if you're an environmental engineering major, you will potentially see this concept in future classes. The other thing that I want to make sure that we're really, really clear about by the end of this lecture is our variable conventions for this class. So anytime you see mass in a problem, mass is represented by m by itself. And typically mass is going to be in kilograms or grams this semester. M with a little dot over the top of it is what we call mass flow. So this is kilograms per second or grams per second. Whenever we see moles, we are going to use N as our variable, and that has units of moles. Whenever we see molar flow rate, we are going to see N with a dot over the top, which is moles per second. Then there are two more that we're going to talk about on the next slide. The first is called X, and this is mass fraction. So this is the grams of a substance divided by the total grams in a specific stream or sample. So when we start to get into problems in this class, we're going to see streams and inputs going into processes that have multiple species. And so the total mass of that stream is that grams total, but then there will be a mass of, say, A and a mass of, say, B in that stream. And that would be going in the top of this particular mass fraction. We'll talk about this more on the next slide. Then the other convention is going to be Y. Y is used for mole fraction. So mole fraction is the same concept as mass fraction, except we have moles of a substance divided by moles total. Definitely pause this slide and make sure that this is super, super clear in your notes. Whenever you see mass, M, mass flow, M dot, moles, N, molar flow, N dot, X is mass fraction, and Y is a mole fraction. And everybody's going to use those same conventions the entire semester. So last thing I want to do is talk about the difference between mass and mole fractions a little bit. So most often process flows are mixtures, right? So if we are looking at something like percent by mass of substance A, in this class, we're going to use X for mass fraction, and whenever we have a species, it's going to be a subscript, and we're going to give it the subscript A because it's species A. Now, we may have ethanol, and we can put ethanol as our subscript, or we can say that A equals ethanol and say that X sub A is the mass fraction of ethanol. Okay, there's a couple different ways to do this, but generally, the species that we're talking about, so the chemical component is going to be the subscript, and then X is the mass fraction. Same thing goes for mole. So when you start to look at your problems for this class, when you read the problems, you're going to see mole percent or percent by mole, and that is going to be a Y with a subscript. So it's going to be Y sub A if the species is A, Y sub B if the species is B. And remember that mass fraction is defined as the mass of something divided by the mass of total. So if we're looking at the mass fraction of A, we're going to take the mass of A divided by the mass of the total. If we're looking at the mole fraction of A, we're going to take the number of moles of A and divide it by the moles total. So make sure that these concepts are really, really strong before you go anywhere else in this video. Last thing to talk about for this particular video is to try and start to apply those concepts. So this is going to be example 3.2, and this is a chemical engineering style problem again. And we want to convert between mass and mole fractions. So this is in your textbook if you want to go look at the actual example, but we've taken some of that text and put it here. We have a solution that's containing 15% of A by mass, which means that the mass fraction of A is 0.15, and 20% by mole of B, which means that Y sub B is equal to 0.2. We then want to calculate the following three things: the mass of A in 175 kilograms of solution, the molar flow rate of B in the stream that's flowing at a rate of 1,000 moles per minute, and the total solution flow rate that corresponds to a molar flow rate of 28 kilomoles of B per second. So these are a little bit different style problems. They're getting you to think about how mole fraction and mass fraction are related. So give this a try on your own, and then take a look at the solution video for example 3.2 to take a look at the answers for these problems. And that's going to finish us up for this particular pre-lecture.